Welcome everyone. Let's learn how to differentiate inverse functions. Let f be 1 to 1 and continuous on an interval a b. Do we remember what 1 to 1 means? The injective functions fx1 is equal to fx2. If this holds, x1 and x2 is equal. So in other words, from my domain, two elements cannot go to the same element in my range. The range of f is an interval I. F inverse is continuous on I. If f is differentiable at x0, which is not equal to 0, then f inverse is differentiable at y0 is equal to fx0, and derivative of f inverse of y0 is equal to 1 over f derivative x0. It is a really helpful theorem. Of course, we have a couple of methods to differentiate inverse functions, but this is also really solid. Let's try to prove the theorem first. We want to differentiate an inverse function. By the limit definition, f inverse y minus f inverse y0 over y0 as y approaches to y0. I can write this as x approaches to x0 this time. I know f inverse y is x. F inverse y0 is x0. This is over fx minus fx0. Since y is equal to fx and y0 is equal to fx0. We can write this limit as x approaches to x0 again. 1 over fx minus fx0. This is over x minus x0. This part is f derivative x0, so this limit is 1 over f derivative x0, which proves our theorem. An example, let fx be x to the fifth power plus x. F is a function from real numbers to real numbers. Be defined. What is inverse of derivative of f inverse 2? We have a couple of methods, as we said. We will use two methods. You can try to figure out the inverse of this function and differentiate that and plug the 2 in after that and find the answer too. But sometimes finding the inverse of a function can be really hard. So we will use the two methods I will show you today. Our first method is, of course, using the definition, the theorem, 1 over f derivative x0. In this problem, our y0 is equal to 2. Our y is equal to fx, which is equal to x to the fifth power plus x. And from here, 2 is equal to x to the fifth power plus x. Everyone can find x equal to 1 from this equation. Instead of working with the inverse function, I will evaluate 1 over f derivative 1. This is equal to, first let's differentiate fx. 5 times x to the fourth power plus 1. Now, to find the derivative at 1, 5 times 1 plus 1, which is equal to 6. So my f derivative 1 is 6. This is the first method. This is how we use the theorem. The second method, you don't need to use the theorem. So let's start with our function. Our function is x to the fifth power plus x. We can swap the inside and outside of the fx of the function f. So inverse of fx. Okay, I said I will swap. I did not. X to the fifth power plus x is equal to x. Now this is a composite function, and when I differentiate this, first I need to differentiate the function itself, and then I multiply this with the inside of it, differentiated of course. So if 5 times 6 to the fourth power plus 1, and I need to differentiate x as well, of course, because I differentiate both sides, so the equation does not change. All right, now I can divide both sides to the second term here, which makes this function is equal to 5 times x to the fourth power. Okay. From here, I need derivative of f inverse of 2. This part needs to be 2. Let's solve that equation. Again, from this equation, everyone can find x as 1. Good. So if I plug 1 for x, I get 2 here. And I need to do the same thing for the other side. 5 times 1 plus 1, again, 1 over 5 times 1, 5 plus 1, 6. So both of the methods we used gave us the same solution. The third method, as I said, you can try to find the inverse of it and then differentiate that. But as we said again, sometimes finding the inverse can be really hard, so we don't really use that method.